When is now? Now is the time to explain time dilation the right way. Relativity can be confusing, but that's mostly because concepts like time dilation, length contraction, and inertial frames are explained using paradoxes, or as I like to call them, bad explanations. In part 1 of this series, I'm going to break down these paradoxes and go a step further to explain what is really going on. You may have heard things like,
when an object is in motion, its time slows down.
The faster you move through space, the slower you move through time.
Moving clocks must run slower. Moving clocks must run slower. Moving clocks run slower.
Therefore, the moving clock runs slow. It is true. Moving clocks do run slow.
But is any of that really true? To understand time dilation, let's first start with the basics of relativity. Special relativity is based on 2 postulates. First, that physics is the same for everyone, everywhere, and that the speed of light is invariant. With that in mind, I'll first explain time dilation using the standard thought experiment. I'll include a space-time diagram here on the side. Al and Bobby start together here in flat space-time. Then, Al launches away at 60% of the speed of light. While Al travels away, Bobby sees him redshifted and watches his clock tick slowly, each tick coming at a longer delay due to the increasing distance. She sees only 2 ticks every 4 seconds. This is the effect of Doppler shift. But if we use a Lorentz transform and look from Al's point of view, Bobby is redshifted and it is her clock becoming more and more delayed. They both see the same thing, the other clock slowing down. But what happens when we account for the delay in the clock due to its distance? What is happening now? Well, for Bobby, this horizontal line is now. 10 seconds has passed for her, and she sees Al's clock has ticked 5 seconds so far. But we can calculate that if Al has kept on his trajectory, he will be 6 light seconds away, and his clock will have ticked only 8 seconds. Time dilation, right?
Moving clocks run slower.
Not so fast. Because speed is relative. From Al's point of view, it's the same story. After Al travels those 8 seconds, he sees only 4 seconds on Bobby's clock and projects that now she will have traveled 4.8 light seconds and her clock will read 6.4 seconds. Bobby's clock is time dilated, not Al's. But both clocks can't be ticking slower relative to each other, right? We have a paradox. Okay, what time is it now?
Time to kick it!
Hit me!
Time to bust the myths. Now we've demonstrated that clocks appear slower when moving away from each other, but we can easily reverse the scenario so that Bobby watches Al's clock for 10 seconds before they meet. In this case, she still calculates that 10 seconds ago he was 6 light seconds away, traveling at 60% of the speed of light, for 8 seconds on his clock until arriving. But during that 10 seconds, Bobby sees the light he sent from even before that. She would see 20 seconds tick away on Al's clock in only 10 seconds. The clock appears to run faster due to blue shift. And it is the same for Al, who sees 16 ticks of Bobby's clock in those 8 seconds. So moving clocks can appear to run faster or slower. What you see depends on relative speed and direction. But what would they calculate? Ignoring what he sees, Al could say that starting 8 seconds before he arrived, Bobby's clock only ticked 6.4 seconds, which makes sense because at that time, Bobby was 4.8 light seconds away. He still calculates that Bobby's clock is running slower, despite the blue-shifted appearance. But is it really running slower? Inertial motion is relative. Any inertial observer can claim to be stationary, so there is no absolute or preferred frame of reference. So when Al calculates Bobby's clock, he is introducing a bias. He is projecting his now onto her relative position. But when Bobby does the same thing, they disagree about when now is. They're not choosing the same now at all. This is known as the relativity of simultaneity. When you see the discrepancy in the diagram, the problem seems obvious. Yet I still hear people argue that the dilation in this scenario is real and that the situation is symmetric. My response is the situation can be symmetric if I look at it from an inertial path directly in the middle of Al and Bobby, at 1/3 of the speed of light relative to them both. A quick sidebar, velocities don't add or subtract the same as for Newtonian physics. We have to use this formula instead. If we transform to this intermediate reference frame, then we very clearly see a symmetry. If we calculate both Al and Bobby's elapsed time at the same instant, the now in this middle frame, then we calculate the same time dilation for both of them. So who is experiencing the time dilation? Neither of them. It is only something we calculate from a particular point of view. Choosing a reference frame creates a bias. The dilation isn't real. Yet. Is it true that moving clocks do run slow? We can calculate that clocks run relatively slow, but the reality is all we've done is take biased measurements and compare them. We coordinated clocks at the first event, where Al and Bobby are together, but then when measuring now from either reference frame, we are projecting out to completely different events. We're not even calculating the same thing. This is why I always give the advice that we have to be very careful about projecting now to anywhere else. The keynote is all clocks run independently. There is no objective or universal time. Likewise, there is no universal now. And this is the root of all the confusion. Does that mean time dilation isn't real? No, it is indeed real. But before we get to what makes it real, I'd like to address another troubling paradox. In 1989, Roger Penrose brought us the Andromeda Paradox, and despite his many brilliant contributions to physics, I wish he had never come up with this particular thought experiment because it is so often bungled. It goes like this. Roger walks past me while I'm sitting on a bench, just, at walking speed. Meanwhile, in Andromeda, the entire Andromedan space fleet has launched for Earth with dubious intentions. This happens now, according to my reference frame. But from Roger's moving reference frame, at his now, the moment in time where they decide to leave hasn't happened yet. It will happen in 3 days. So will they launch or not? Can they change their minds? Is there any uncertainty? Let's clarify a few details. First, we're assuming I'm stationary relative to Andromeda, ignoring orbits, galactic rotations, and the expansion of the universe. This is just for convenience. Second, we don't actually, yet, know anything about the Andromedan space fleet. The light from the moment they left Andromeda won't even reach Earth for 2.5 million years by Earth's clock. Third, when the light reaches us, assuming we've hung around that long, we won't see anything different. We will see exactly the same thing, the fleet leaving Andromeda. If you ever hear someone explaining the Andromeda Paradox mention seeing different things, they have completely bungled the thought experiment. And finally, we assumed Roger was walking away from Andromeda. So when we transform from my frame to his, the event 3 days before they decide to leave moves into Roger's now. If he is walking towards Andromeda, then his now actually jumps up to 3 days after the fleet has already left. If he is walking perpendicular to Andromeda, then the transform is practically negligible. The reason for the difference in now is obviously not due to Roger's incredible walking speed. Rather, it is because Andromeda is 2.5 million light-years away. When we transform even the tiniest bit out of my stationary frame, the difference in now is magnified by projecting it to somewhere so astronomically far away. But what have we learned about projecting our now to some faraway location? The key here is that the discrepancy only comes about because we are projecting now from a different inertial frame over a massive distance. But that now isn't real. In fact, if Roger stops and starts walking, his now projected to Andromeda keeps changing, hopping back and forth, with no effect whatsoever on the reality of the Andromedan fleet heading towards Earth. If he runs back and forth at really high speed, like the Flash, he can swing his now to extremes, nearly 2.5 million years earlier or later from mine. But none of that changes reality. The stationary frame of Earth will still have to wait for the light to reach it before it can see the fleet leave. If Roger went zipping about at 90% of the speed of light while I waited stationary for 2.5 million years, he wouldn't experience as much time. This is, of course, the twin paradox. I've already made a video to explain that. Spoiler, it depends on the total path, not just the relative speed. In that case, the time dilation Roger experiences is real, but we can easily measure it because we start and stop at the same place, with the same now. We don't have to project anything to somewhere far away. There's still one more explanation of time dilation I feel the need to address. Light clocks. What's a light clock? A clock that bounces light back and forth to measure time. Someone will inevitably argue in the comments, doesn't a light clock have to run slower when moving to preserve the speed of light in all reference frames?
Moving clocks must run slower.
The argument is the moving clocks run slower because the light must follow a longer path. See the diagonals? But there is a lie here. The video shows slices of now in the stationary clock's reference frame. This spacetime diagram shows the horizontal lines of now used to generate each video frame. Do you see the problem? It's a biased video. It is defined from the stationary frame, frame for frame. If we take a video from some middle reference frame, we can make the clocks run at the same rate, frame for frame. But neither of those would be true videos because we don't account for the delay of the light reaching the camera. Rather, if we take a real video from where the moving clock is headed, we see it run faster due to Doppler shift, even though it is moving. The relative rate of the clocks is an illusion based on reference frame and projecting a biased now in our calculations. When we take away the implied now of a particular reference frame and stop projecting that false now, we can start to understand why this way of describing relativity is so confusing. The problem is calling the horizontal line now, or any of these lines now. That one simple assumption leads to so many bad explanations and confusion. So I say this again to all physics educators: stop calling this line now. Is time dilation only an illusion? Absolutely not. It is real. The twin paradox proves it. My point is to break down all the bad explanations of time dilation and provide a basis for better intuition about relativity. Back to the original question then, when is now? Well, you can only say when now is for you, locally. Now has a meaning for here, but not so much for anywhere else. But if we think about it a little, we can see that now can still have some meaning. In my light cone, there are three regions: the past, the future, or possible futures, and all of this. This region could be now for me, depending on my inertial frame. But I suggest we stop ever calling a particular line now because of all the confusion it creates. Instead, now for anywhere other than here is all of this. Now, because of the Lorentz transform, the time difference between my here and now and somewhere just across the light cone is an arbitrarily small instant. That is to say, the moment right after now. The same is true for the past. Just near the light cone is the moment right before now. So what comes between the moment before now and the moment after now? Now. But of course, it can't be now in any kind of absolute sense. From the point of view over here, for example, all of this is now. It seems like a contradiction until you remember that you can't reach any of that now without violating the axioms of relativity and traveling faster than light. So you can't change any of that or affect it in any way. You won't even get any light or information about it until later, when the light finally crosses our path. When is later? Later is when I will release part 2 and explain why length contraction is also an illusion. Let's recap. This line isn't now. The Andromeda Paradox isn't a paradox, just a bad explanation of the relativity of simultaneity. And moving faster doesn't make your clock tick slower. You are just projecting your now into a different relative space-time coordinate. Clocks run independently, there is no universal time, and time dilation is real, but depends on complete space-time path, not just relative speed. To understand how time dilation really works, check out this video on the twin paradox. And of course, subscribe and stay tuned for When Is Now, Part 2, Snakes on a Train.